So hello everyone, this is week 3 of the course Non-Newtonian Transport Phenomena of Non-Newtonian Fluids, which is offered from Swayam, and this course is actually PG course, which is postgraduate course. And what I am today telling you is that whatever has been taught in this particular week, which is third week. So in the first week we started with this basics of non-Newtonian fluids and how this fluid is different from Newtonian fluid, and at the same time this basic governing equation that will be used. For example, this fluid mechanical governing equation starting from the continuity equation and then Bernoulli's equation, and later you started with this momentum equation. So those basics are in line, and maybe in the next week it is going to be revised again. So let me just fix it. You are presenting to okay, so let me just present my screen. I think I am in presentation mode, right? So in this week we will be solving these questions. So let me take you to the main thing. So this was the third week, which is rheology measuring instruments for this. I mean, 2. So you see, in the first week you started with this Newtonian fluids and classification of non-Newtonian fluids, and how they have been classified based on time independence, non-Newtonian fluid, time dependent non-Newtonian fluid, and the viscoelastic fluid. And the fourth lecture was entirely on the viscoelastic fluid side, right? And then in the week 2 the measure thing came, which is the rheological measurement of the non-Newtonian fluid. The rheology measuring instruments are being utilized for the same, and this rheology measuring instrument, what it is doing basically, it is helping you to get the stress versus strain correlation for your given fluid, whether it is Newtonian or non-Newtonian, right? So the capillary viscometer was the one in that, and in that we have also seen that how different errors are there while handling the capillary viscometer, and how those errors can be rectified or corrected through mathematical manipulation that has been discussed in the week 2 of the course. And in the week 3, especially another kind of rheology measuring instrument, which is this rotational rheometer, have been discussed. So here you got to know about this plate and cone type rheometer, and then this two plate type rheometer, which is this rotational viscometer, and then these questions you have been given. So in this particular class what we are taking is, I will be helping you to actually get through these questions, and this lecture will be helping you to solve these questions. For example, if you see, the first question is around this concentric cylinder viscometers, right? And so what I will be doing, first half of the class we will be actually revisiting to the main bullet points that has been taught in the entire week by the sir, and then we will be looking at some calculations where sir was a bit fast, so that it eases out entire conversation. And then we will be solving some questions which are similar to the question that are given to you, but not the exact question. So definitely whatever we will be solving today, it will help you to solve the questions that you will be probably finding in your examination and in this assignments, right? So let's begin with the revision of the lectures that was there. So in the first week, as you can see, let me just fix it for you. So it's like, yeah, let's keep it here, right? So first you had this recapitulation of whatever thing you got to know in the second week, where the second week was mostly about this. Let me just fix it. Yes. Now it is coming. Yes. So about this capillary viscometer for rheological measurement of the time independent non-Newtonian fluids, right? You just keep this point in your mind, because here the time independent non-Newtonian fluid has been mostly analyzed, but with the in till now, after the study of the third week, you may be knowing which instrument you are going to use for this viscoelastic materials, which are viscoelastic non-Newtonian fluids, right? So as you know, this shear stress calculation that was there, you got the formula that tau w equals to minus del p by l r by 2. So from here what you conclude is that the wall shear stress is depending on the pressure difference, right? And then this shear rate is depending on this uh, uh, 8v by d. V is the average velocity flowing through the this capillary which is there, right? So, and there's 3a and s plus 1 by 4 and s, and this and s has been calculated using this d log tau w divided by log 8v by d. So mostly you are going for these graphical measurements. Mostly you are actually utilizing this tau w by 8v by d versus curves log on log scale, and then you are measuring the slope to have the number and quantitative measurement of the and s value, and this and s value is giving you the factor which is actually coming because of the time independent non-Newtonian fluid nature of the material. For example, if it is only Newtonian, then there will be only 8v by d, right? Which is the one case. And then there are different sources of errors possible in the capillary viscometer, and these errors can come because, as you know, when it is entering the capillary exactly there, this error due to end effects can cause increase in the pressure drop at the entry, and that may lead to some kind of measurement if these errors are not considered during the calculation to have this shear stress versus shear strain curve, right? So correction for the entry effects, that is tau w equals to minus del p minus delta p e divided by l r by 2, right? And then this error due to apparent sleep. So this is another main factor, and mostly this is the factor which is responsible for this large deviation in the error, right? Actual value at wall leads to non-zero velocity at the wall, and this sleeping uh, nature at the wall it can be corrected by inducing the sleep velocity and subtracting it through the to the actual calculation that you had, which is at v by d, right? So now we will be starting the revision for the concentric cylindrical rheometer. So in this one, if you see, let me just keep it somewhere. If I can sort it down, yes, it can be sorted. Okay, let's make pin my screen. Okay, it's right, no issues. Let's reframe it. Pin to screen. Yes, so it is here. So if you see that in the present days, majority of the commercial rheometers are based on concentric cylindrical geometry, and in that also, if you see this, that Kuwait in 1890s is the first developed a rotational rheometer that was based on this concentric cylindrical geometry, right? And the main funda which is actually utilized for measurement of the rheological properties of real fluid which are mostly non-Newtonian, whatever we are using day to day life, starting from the milk, honey, soap solution. If you see the honey, for example, you can actually feel the apparent elasticity associated with the large viscosity of the honey, right? And that is another point which actually lets you know that it is somewhat different from the Newtonian fluid, which is water light, but it actually stores the memory. For example, if you have applied a stress or shear at a given time t, then at t equals to t plus 4t, there will be memory of whatever stress you have applied at t, right? So the main thing that is there is the shear stress related to the torque that you have to measure uh, uh, with this rotational rheometer. And if you see, if something in the meet tab needs your attention, okay, go to meet tab then. So yes, and another one is this, utilizing these rotational rheometers, what you can do is you can measure this shear rate related to angular velocity, right? So let me just keep it here only. How I can keep it? Okay, let me keep it like this. Okay, so if you see, the basic geometry of this rotational rheometers are, there is one is static outer geometry. You can see the outer part of the cylinder, and then there is an inner part, and in most of the cases this inner part rotates, keeping the outer part static, and the fluid is in this annulus region, which is getting seared through the rotational speed provided to the inner cylinder. And under that condition you are actually going to measure the rheological property of the fluid. So in this, the basic assumptions that is there, first is this: you have to consider flow of the fluid confined between the concentric cylinder with the inner cylinder rotating. So there are different cases where when the outer and inner both are rotating, or there is the this relative rotational velocity difference between the same, that are different thing that will be taken care in the upcoming slides. But the main thing is to keep the thing simple here. What you are having, this, the flow is steady, laminar and isothermal, so there is no temperature effects associated with any of the fluid rheological property. And then this v theta equals to r omega. Omega is the rotational velocity of the interior cylinder that you are having. So this is only existing. Rest velocity component, which is in the r direction or which is in the z direction. Z direction is upward, and r direction towards the radius of the cylinder. Those are assumed to be zero. And then there is no effect of gravity. There is no effect of end effects are not there. End effects means at this end or at that end, because of the meniscus formation, if there is some changes, those are not considered. So symmetry in this theta direction, so you can consider this as a SG symmetry problem where this is rotating. So anything happening this side, the same will be happening opposite side. So that has to be taken into account, and you need to actually have a simplified system that can be achieved by considering the entire problem in axisymmetric geometry. So now I will be taking you to the main equations. So these are the governing equation, which is first is the continuity equation, and another is the r directional component of the equation of motion. So this entire problem you are solving in r theta z, right? So now it's it's the cylindrical geometry, and these equations you don't have to get yourself intimidated by this big equation, because this you can actually follow up any books, transport phenomena, basic transport phenomena book like BSL. So from there you can take the equation and then analyze or use these equation according to the need of your problem. So anyway, if the questions are being provided to you, these equations will be provided. You don't need to memorize these equations, but yes, you need to understand these equations. For example, what are the effects each terms are having. So for many people it becomes very easy to have understanding over different terms when you are dealing with this Cartesian coordinate. But once you are moving into the cylindrical coordinate and then spherical coordinate, curvilinear coordinate system, then it sometimes becomes difficult how these terms are coming up into the picture and then how these will be used. So this is the first example of whatever will be mostly used in this entire course. And now if you see this, the continuity equation, which is del rho by del t plus 1 by r del by del r vr plus 1 by r del by del theta rho v theta plus del by del z rho vz equals to 0. So if you see, we have seen that the problem is steady state, so there is no transient effect associated with it, right? It means there is no dependencies associated with the time. So that's the one thing. And then this del rho by del t term become 0, right? And then another term which is 1 by r del by del r rho r vr. So those things are taken care. So vr is 0, so this term will be also going nullified. And then this is getting nullified because of this del by del theta axis symmetry is there. So third term also gets nullified. So only term you are sitting with is the fourth term, which is del by del z rho vz equals to 0. So continuity equation gives you that this vz velocity is independent of z coordinate system, right? And then the r directional component of the equation of motion will be giving you. So once you apply this steady vr is 0, then v theta is existing, but del vr by del theta becoming 0, that's why this term is becoming 0. And then this minus v theta square by r, this will be there, this will not be omitted anyway because we don't know anything, and it will be actually having some influence on the overall rheological property of the fluid. And then this vz del vr by del z, right? So in this del v, this vz is 0, right? So this minus del p by del r we will be keeping because we don't know anything about that. And then 1 by r del r tau rr by del r, this is normal component of the shear stress that has to be this will be actually giving you the differences in the normal velocity, normal shear stresses, right? Which are the main part of this non-Newtonian fluids, and especially for the viscoelastic fluid, because these normal stresses are not getting nullified, or the differences between the normal stresses are not getting nullified, and that actually leads to what we call is Weisenberg effect. So the Weisenberg effect, if you remember, is something that a fluid actually let me just show you that Weisenberg effect. If I can show you, let me just see if it is there.
Mechanism,
So let me just
mechanisms which are leading for the transport.
we just put that here. So it is a bit slow. Weisenberg effect, right? So so we will be obviously acknowledging whatever video we will be using. Just see what is happening here. So add is there. Just so what actually happens when a non-Newtonian viscoelastic fluid is there? You see this video. Let me just expand it for you. You see this video. Once this rotation is happening, fluid is climbing with the rod. Why this climbing phenomena is happening? You are not shearing the fluid in the perpendicular direction, rather you are just rotating. Still the fluid is coming up as if it is carried by the rod in the vertical direction, right? So why this is happening? So we are going to discuss the same, that how this is happening, right? So these are the component, which is this del theta theta sigma r or sigma theta theta. These are the components that are actually leading to the vertical motion of the fluid, and then this is the normal stress in the gap, where sigma is sum of this p, which is normal pressure, and then tau, diverteric stress, right? And then in the theta component of the equation of motion, you can see that this similarly for the theta component, you can have this steady state assumption, and then this del vr by vr becomes 0, v theta will be there, but because of the asymmetry nature, del v theta by del theta will be becoming 0, and then you will be having this particular coming up at the end, which is del by del r square tau r theta equals to 0. And this will be giving you information about the shear stress in the gap. In which gap? In which gap I am talking about? In this gap, which is between the static cylinder, which is outer cylinder, and the rotating cylinder, which is the inner cylinder. So this gap, in between this gap, there is this in between this gap, if you see, let me just expand it. In between this gap, there is this shear, this del v theta that was there, this shear stress you will be actually calculating, and it is actually coming from the second theta component of the equation of motion that you are solving. So this tau r theta will be actually computed based on that, and then the z component of the equation of motion will be giving you this this hydrostatic measurement. So anyway, these gravitational effects you have considered or nullified. Based on that, you have to actually manage this particular component of the equation of motion. So in all the three dimensions, you are actually solving the equation of motion. The main equation you are anyway referring from any book, but the analysis is done based on the assumptions that we have made in our first slide, which was here, like steady, laminar, and the isothermal flow, and then whatever boundary condition you had, that was the main thing. So the boundary conditions here, whatever will be used, is that at r equals to ri, which is the edge of the inner cylinder, you are having this velocity in the theta direction, which is this v theta rho this omega into ri, right? And then this r equals to r0, v theta equals to 0. So yes, so anyway, let me just see if things are going well. So let me just see. Yes, so you can also comment, right? So comment is open. So anywhere you are having any doubt, or anyway, the forum you can also use. So if you know that, you guys can ask questions at different levels. So for example, this is Q&A session, so you can be using this. So discussion forums can be used, and based on that you can clear your doubt. And these assignments, whatever you are facing any problem, these regular problem solving sessions are there. So whatever sessions we are having here right now, it is the third week. All the videos you can find in this particular section, problem solving sessions, which are happening weekly, in order to ease out the difficulties that you are facing in learning the concepts in the running week. And it is actually good to have one-to-one discussion rather going through video every time, right? So this v theta equals to rho z, this omega r0 at r equals to r0, right? The main thing is this rotational component, which is associated with the inner cylinder. There you are taking this r equals to r0, right? And then if the both cylinders are rotating, then v theta equals to omega naught r0 at r equals to r0. So it's just basic v equals to r omega implementation in order to have the theta component of the velocity. And once you solve the upper theta component equation, which was del by del r square tau r theta equals to 0, you will be getting that r square tau r theta equals to constant and this constant which is C1 coming up in order to get the shear stress is depending on the torque, right? And why this torque is arising? Because you are rotating the fluid with a given rotational velocity which is omega, it is leading to a torque within the fluid, and that torque, if you measure somehow, then you can measure the shear rate or shear stress, right, which is tau r theta, right? So this torque measured on the inner cylinder is mi. So this mi you remember, because we will be anyway using this. So mi divided by ri equals to tau r theta ri 2 pi ril. So this torque is actually getting the origin of this torque is coming from this shear stress, right? And this shear stress is acting at what uh, I mean area? It is 2 pi ri into L, right? So let's now solve a question, and then we will be actually coming up with this, because mathematically it sometimes becomes difficult for you, then it is good to have. So let me just add it, because this control M is not working, right? Yes. Huh. So in this particular question, what is given? Just see, concentric cylinder viscometer of dimension Ri. The inner radii is given as 20.04 mm, and by the way, these values whichever is given, these are a bit realistic. So all these values are as per the instrumentations which are being used in day-to-day experimental activities in the laboratory and in industries, right? So this Ri equals to 20.04 mm, and then outer velocity, which is Ro, equals to 73 mm, right? So what is the difference between 73 and 20.04? If you see, around 53 mm of the difference is there, and that is the region where you are going to calculate this tau r theta, which is the shear stress in that particular annulus region where the fluid is actually resting. And the length of the entire thing is let me just see how. So suppose this is this outer cylinder, right? This is outer cylinder, and then the inner cylinder I am drawing with blue color. Let me just have blue color. How I can just fix it? Eraser, I just want to, yes. So this is this inner cylinder, right? Somehow eraser should go. Okay, so this is your outer cylinder, and this is your inner cylinder, right? And then this inner cylinder is rotating with omega I, omega rotational velocity, right? Rotational velocity, right? Or speed, you can say. So this is the reason. So in this particular question, it is given that this is around 20.04, right, mm, and then this outer is given as what, 73 mm, right? And the entire length of the tube, what is the length is 60 mm, right? So this is the instrumentation and the dimension of the instrument. So it is used to investigate rheology of an unknown liquid. You don't know the liquid. By rotating the inner cylinder at, what is the value of rotational speed? It is 10.49 rad per second, right? So 10.49 radian per second is the rotational speed of the 10.49 is the rotational speed of the inner cylinder, right? So let me just see. Yes. Okay. So The main thing is, if you see this, the corresponding torque is the value of torque, you know. So we were discussing about the same, that mi, which is the torque value, is given as 29.7 into 10 to the power minus 4 Newton meter, and this anyway you will be calculating through the instrument. So for the calculation purpose, it is given in the question. So what is the value of wall shear stress? Okay, so you have to solve this tau r theta, wall shear stress value, right? Or this L, for the given L, how you are going to solve it, right? So this wall shear stress that we were having conversation about, this one, let me just come to that. This wall shear stress that you was getting from this is this tau r theta. So this tau r theta, once you calculate it, so you got to know that this torque is measured on the outer cylinder and the inner cylinder, both you are measuring the torque, and then this torque, this C1 value will be related to the torque anyway, right? So depending upon the gap, so the gap between the inner cylinder and the outer cylinder, the gap is actually will decide the accuracy of the assumptions that you had, and then which equation you have to opt for in order to have the accurate solution, right? So there were many conditions that has been talked about. I think 4 conditions. First was this, for very narrow gap, which is k equals to ri by r0 greater than 0.99, right? So very narrow gap means the inner cylinder radius is 0.99 times the outer cylinder radius, right? So if you see this in your problem, what you have to find to actually go for the problem is this ri by r0. So if you see that ri by r0 value for your particular this particular question, then you will come to know that which particular equation will be actually satisfied for this particular question. And then what I'm suggesting is the wall shear stress, right? The wall shear stress, right? The wall shear stress using the one that is given in the question, concentric cylinder viscometer, right? Concentric cylinder viscometer, or rheometer sometimes people call it, viscometer, is given by, sometimes people write it tau ri, or sometimes you can write it r theta. So that tau is given by the rotation, which is torque m divided by 2 pi L into r. So you know this, and where this is acting, if you see, this is acting at ri distance, which is the inner cylinder. Here at this wall it is acting, right? And at this wall, if you calculate this particular value, so all the values you are given with, so m value you are given with, m is what, 29.7 into 10 to the power minus 4. So 29.7 into 10 to the power minus 4. Okay, what was the unit of this? Newton meter, right? Newton meter divided by what? 2 into 3.14, which is the value of pi, multiplied by L. L was what? L was 60, right? And then your RI. RI was what? 20.404. That you have to convert into meter. So 20.404 into 10 to the power minus 3. So it is square of that. So it is square of that. So what I am saying is, this particular discussion that we had is this one, 2 pi ri square L. So 2 pi L ri square. So inner cylinder you are actually measuring the torque, which is this tau r theta. Okay, so if you do so, this particular calculation, once you solve, you are going to get what? 19.63 Pascal. You can use your calculator, because calculators will be allowed in the exam. So 19.63 Pascal is the answer that you are going for, right? 19.3 is the option A. So option A is correct answer, right? Option A is right. So the main logic about this question was, if you see that this Ri, so what you have to get before going for which formula or what you have to use. So you have to calculate the ratio of Ri by R0. Okay. So once you see the ratio of Ri by R0, which is K, and when you calculate this 20.04 divided by what? 73. Okay. So what you will get? 20.04 divided by 733. What you are going to get? If you see, you will be getting something very small, right? Okay, 20.03 divided by 73, right? 20.04 divided by 73. So you are getting 0.2745, right? 0.2745. 0.27. So it's coming 0.2745 means anyway 4, right? So this, what you are getting is your inner cylinder is 0.27 times that of outer cylinder diameter, right? So you got to know that the value of the wall shear stress is in Pascal unit, which is 19.63 acting at the wall. So now we will be solving similar question, but somewhat different. Why the second question is different from the first is the one that is here you are asked what is the value of wall shear stress in pascals, right? So if you see that this question 20.73 L is what? 60, and this concentric cylindrical viscometer, and this is concentric cylindrical viscometer. Anyway, what is the difference then? Same question is there. Here this torque is different in the third problem, right? And then 20 and 20 rad. Yes, 20 rad is another thing which is different. So for the high shear rate, high rotational speed, you are going to solve afterwards. Okay. And then you see in the third problem again, these are very similar. One is this 20.04 and another is 20.08. Means very narrow gap is there. And if very narrow gap is there, then another kind of calculation is needed. Okay. So what I am thinking is the second problem you may change. I think some calculation issue is there. So in the second problem, just one correction will be there. Is this R0 is what? 20.08, right? Yes, it is 20.08 and rest is I think same 20.08. Okay, so this is correct now. 29.7 into 10 power minus 4 and then this 10.49 red. Nothing is wrong now. So same thing you have to find now under this situation. So then we will be having discussion about the same. So you just follow this. So these videos anyway are being recorded, so you can actually revisit these videos once you are solving your assignments. But the main thing remains same again. First, go through the videos which are being provided weekly. It is better to watch one video per day and then next day another video, and in between you should have a short revision of the same, because you have to understand the approach, because here these are advanced fluid mechanics course, and here you will be anyway actually following or referring the books. That is the one thing. So you don't have to mug up the equations over here. Rather, you have to actually understand the approach and then you will be utilizing your approach for the problem solving assessments, right? So if you see this particular question, before that let me just complete the revision of this first. It's like 8 slides are remaining. So here, till now you got to know that how you are going to calculate this shear stress, right? So this shear stress is tau r theta, which is r I 2 pi r I l. So once you multiply this tau r theta with this particular factor, it will give you the torque divided by Ri. So this torque divided by Ri, what it is doing is, it is actually helping you to actually relate the compute the constant which was required and which came once you calculated the theta component of the momentum equation, and then through that you calculated the tau r theta, right? So now the entire calculations that you are having, and the next question we will be solving based on this only. When the gap is very narrow, the question that I just corrected, when the gap is very narrow, for example, the one that we are going to solve now, let me just show you that this one here. If you see this, the value k, which is this Ri divided by R0, right? And once you solve it, 20.04 divided by 20.08, right? Once you solve this 20.04 divided by 20.08, where is this? So you will be getting very small number, right? 20.04 divided by 20.08, right? You will be getting very small number, which is 0.998, right? So it's 0.998. So very small number, 0.998. So let me just tell you here, the inner radius is 0.998. It is almost 1. So this value is almost 1. Means Ri is almost similar to R0, right? Ri is similar to R0. Okay. And this, if you see, this Ri is similar to R0, 20.04 divided by 20.08. And in the under this condition, if you see that it is not exactly similar, rather you can say that the gap between the two cylinders are very narrow. Still the inner cylinder is rotating with the rotational velocity of 10.49 rad per second. So the inner cylinder Ri is rotating with what? With rotational velocity of what? This 10.49 radian per second. Okay. So if you see this, let me just set it down. So so this particular thing, if you see this, when it is very narrow, the gap is very small, the curvature can be neglected. So it's like you are walking on earth, right? It seems that the earth is flat, so the floor is flat, but when you came to know that the earth is having its shape spherical, it's the it's actually the change compared to the overall geometry. So here if you see that when the gap is very narrow, curvature can be neglected, and thus shear strain, which is gamma, this gamma can be written as del x by del r. So this del x by del r, if you can see that this, let me just show you. So what I'm saying is, this is shear rate gamma, which is written as del x by del r. Okay. and this can be written as r I theta divided by r0 minus ri, right? Why? Because this, you know that angle equals to arc upon radius, right? So then this arc can be written as radius into angle. Arc equals to radius multiplied by angle. Angle say alpha. So this is radius multiplied by angle. This is theta right here. So this is the cylinder that is there, and this cylinder is rotating. Okay, but from the top when you see, there is one cylinder and then there is another cylinder in between, and then this cylinder is rotating with rotational velocity omega, right? So what it is saying is, when the gap is very narrow, this change which is happening delta x because of the the rotation will be very small, and that can be written as, you can write that arc is nothing but angle multiplied by radius, which is coming out to be this, and delta r is what? Outer radius minus inner radius, which is r0 minus ri, right? So if you see this particular conversation that we are having, this theta r divided by r0 minus ri, so this theta ri you are not taking, where you are calculating your strain at the midpoint between the two cylinders, right? So what I'm saying is, let me just revisit the same, this one. So this is your inner cylinder, this is your outer cylinder, right? And then this inner cylinder is having radius what? ri, and then outer cylinder is having radius what? r0, right? So this difference r0 minus ri divided by this r0 plus ri, right, divided by 2, this will be nothing but this particular arc, right? Suppose inner cylinder radius is 3, outer is 5, so 3 plus 5 is 8, divided by 2 is 4. So you are coming somewhere here, right? Every time when you can just take some numbers for this, and you will come to know that this r0 plus ri by 2 is nothing but the midpoint between this cylinder and that cylinder, right? And this midpoint is the point where you are actually calculating your shear rate, and this shear rate will actually tell you some information about the non-Newtonian property of a fluid, whatever fluid you are considering and under your consideration or experiments that you are performing, right? So if you see this, what I'm saying is this one, the question here, you had this 0.04, which is r 20.04 is the inner, and another one is 20.08. So very small gap is there between the two, and the length remains same again, and the rotational velocity also remains same, and the torque also remains same, right? So now the wall shear stress, what will be there? So one thing is clear, that now the v theta velocity will be high because the gap is very narrow, right? So this, if you see, let us solve this question. No, just revisit this section. So this r is what? Midpoint between the cylinder, which is r0 plus ri by 2, and similarly you can calculate the velocity gradient is constant across the narrow gap. Thus shear rate gamma, which is del v by del r, okay, the gradient of the velocity is omega times r bar divided by r0 minus ri, right? So this was theta times, and this is omega times, right? So now you can see that you can calculate tau r theta versus gamma dot information, and this is available to determine the rheological behavior of this. So now you know that tau r theta you was knowing from the expression that we had before, and then now from this one, which is omega r bar by r0 minus ri, you are having this shear rate. So shear stress you have computed, shear rate you have computed, and based on that you can actually decide what you have to do. In the last lecture, if you remember, we have already discussed, let me just open that, this properties of fluids, let me just open that slide. It is here only. So no, it's not here. So it is week 2, the curve which is actually giving you differences between different fluids, right? So if it came, it is not coming up, right? Okay, yes, it will come anyway. Yes, this one. So let's take this to the current week slide. Okay, here. And then let me just close because it will be actually lagging. Okay, so let's cut it. Okay, so here if you see this uh, entire spectra of the different fluids, if you see this when n equals to 1 is what, n equals to 1 is what, the Newtonian fluid that you are having, and then n less than 1 and greater than 1, and then this tau naught plus mu del u by del y kind of behavior, and sometimes tau naught plus mu del u by del y to the power n power law behavior can also be shown with the second term of this Bingham plastic fluid, right? So these can be decided based on shear stress versus shear rate data that you are having. Okay, so if you see this one, so the main thing is for different radii ratio, you are having different expressions for this shear stress and shear rate, right? Basically shear rate, you are having different expressions, right? And that different expressions you are utilizing in order to get the insights. Okay, so let's solve the question that we were solving. So it is the second question. Okay, so in this one, if you see, gap is narrow, so this is inner cylinder, this is outer cylinder, and this is narrow, right? Narrow gap. So the gap is narrow, and if you see, let us calculate. First, we have to find K value. Then, accordingly, we will select. We'll select K is what? Ratio of radii, right? Inner to outer. Select shear rate equation, right? Shear rate equation. Okay. In this case, here K is what? K equals to Ri divided by R0, right? Ri divided by R0, and then this Ri divided by R0 can be calculated 20.04 divided by 20.08. Okay, then you will be getting 0.998, which is greater than 0.99, right? Thus, so what? So what? You can actually neglect the, if I can pin it. Yes, it is okay. So if you see this, so if you see this, uh, the ratio, you know, now based on that you came to know that the curvature effect, thus curvature effect can be neglected, and the shear rate equation in this case we will be considering gamma dot at Ri. Okay, let me just write it again. Okay. At Ri is equals to the rate of change of velocity to the rate of change of radial dimension is give you omega Ri, omega R bar divided by R0 minus R, right? So it will give you R bar is what? 20.04 plus 20.08 divided by 2, 20.06 mm. R0 minus Ri equals to 20.08 minus 20.04 equals to 0.04 mm, right? So if you see this, let's keep it here. So what you are going to get is this gamma dot Ri equals to del V by del R by R0 minus Ri. So all the steps I am solving so that it becomes easy for you to follow. So here if you see that 10.4906, right? Okay, so it is 5260.74 S inverse, right? So this is the one thing. So you are getting 5260.79. Okay. So let me just change the options also, because these options you are not having here. The wall shear rate at the midpoint of the MS region. So this question, we just put it here. Okay. So I think this question I have not had it here. Let me just, because it is here only, so just snip it and put it. So it's like this is that second question, right? Let's just, I can just keep it there because this question you have to rectify. Okay, so I will just keep it there. So this was the question. Second question is entirely rectified. So this second question you have to actually consider, right? This particular question, what I actually changed it. So some a bit error was there. That error I have just removed and rectified, so now you can follow it. Okay. So no outline, I would say. Okay. So no issues. So this was the question that we were solving, and you can just remove this question. This is wrong. Second question is this one. This is question number 2, and question number, you just miss it. We will see which question it is. It is the similar. We have already solved, right? So now the third question, if you see, is the third question, and before moving to the third question, let's discuss the third case. Okay, so in the third case, if you see, this Ri by R0 is less than 0.1. Okay, so means Ri is less than 0, is 0.1 times of less than 0.1 times, right? So in that case, different correlation of the shear stress and rate you have to utilize, and again this power law behavior is there. So let us solve this question. So in this question, if you see this, concentric cylinder, viscometer of dimension Ri equals to 20.04, right? And then R0 equals to what? 20.08, and the length of the cylinder viscometer is what? 80 mm, right? Has been used to investigate rheology of an unknown fluid by rotating the inner cylinder at 20 rad per second, and the corresponding torque is 60 into 10 to the power minus 4 Newton meter, right? What is the value of wall shear stress at the inner cylinder surface, right? So wall shear stress at the inner cylindrical surface you have to actually calculate, and that will actually tell you about the ease of utilizing these expressions in order to get the geological data about the unknown fluid. So this thing we will be anyway putting it in the, let me just put one new slide here, and I will just remove the layout. Okay, I will just clean it up. So in this one, if you see that cylinder is like this, okay, Ri equals to 20.04 mm, R equals to 20.08 mm, L equals to 80 mm, right? Okay, L equals to 80 mm. Let's just open this. L equals to 80 mm, and then L equals to 80 mm, and if you see this, the rotational speed which the inner cylinder is rotating is what? 20 rad per second, right? And then torque, which is mi, which is measured, is 60 into 10 to the power minus 4 Newton meter. What is the value of wall shear stress at the inner cylinder? Okay, inner cylinder is arched, right? So when you actually calculate these parameters, then you will come to know that for this particular thing, when this here you can utilize the wall shear stress using concentric cylinder rheometer is tau Ri equals to m divided by 2 by L R I square, and this will be what? This will give you 16 to 10 power minus 4 by 2 into 3.14 multiplied by 80 into 10 power minus 3 multiplied by 20.04 into 10 to the power minus 3. So it will give you what? 29.74. So here also 29.74. In the first question, I think you had something else. So you see that these values are giving you some hints, like how the narrowed gap. So when you had narrow gap, you are having what? More walls here. Then the one which was one. So in the first question, if you see, let me just put it here. Ah. In the first question, if you see that you had this 19 something, 19 na 19.63, because the gap was high. So there is this v theta component of the velocity is having the rotational speed is anyway same. So now with the narrow gap and the same rotational speed, you are going to have the more shear. Okay, and that is reflected by the value that you got in this particular question, which is the third question. Okay, so you got this 29.74 is the answer. So now let us see the next question, which is cone and plate geometer. So now the first lecture we have revised and we had some questions around. So this second question is on the cone plate, and which is the central lecture of the last week. The second lecture that we are going to revise. But if you see this cone and plate question, and through the questions we will be anyway revising it, right? So this cone and plate rheometer having this 25 mm radii and cone angle of 1 degree 18 minutes and 45 seconds is used to investigate the rheology of an unknown fluid at room temperature, right? When the cone is rotated at 0.1 radian per second, the corresponding torque is 3.97 into 10 power minus 4 Newton meter, right? What is the value of shear stress at the lower edge of the cone in Pascal? So the lower edge of the cone means, they are asking the value at this. If you see this is cone and plate geometry. Anyway, these angles are very small. Okay, this tapering is very small. So this here we have to calculate the shear stress lower edge of the cone. Okay, so if you see this lower edge of the cone, and so let me just get it here, right? Okay, so let's make it narrow. Yes, so if you see this okay, if you see this, the next, it is there, this one, the 9th lecture. Okay, so here you had the recapitulation of whatever you learned in this first week, where you came to know about this torque measured on inner cylinder. Okay, as concentric cylinder rheometers you have. Then there will be there will be disc type rheometer. One static disc and another one is this rotating disc, right? And then this what I'm saying is cone and plate kind of setup which you got to know. Okay, and each have their own advantages and disadvantages. Using cone and plate, it becomes easy for you to actually calculate the differences in normal stresses, right? And this differences in normal stresses will actually help you to actually estimate the rheological behaviors like Weisenberg effect and those things, why they are arising, right? So concentric cylinder rheometer for rheology measurement, you got to know about the inner cylinder torque, outer cylinder torque, and then there was this cases when the gap is very narrow, when the gap is this Ri by R0 is less than 0.99 and then less than 0.1, which is the larger end of that. What shear rate expressions you are going to, shear stress expressions remain same, right? And sometimes you have to go for this graphical measurement, and then that's for the fairly narrow gap, which is 0.5 to 1, what approach you are going to use to calculate this. Okay, so normal stresses in fluid flow. So on rotating elastic liquids, they climb, the video that we have seen just now, they climb rotating cylinder, whereas surface near the surface near the rod is slightly depressed for the Newtonian, right? So this climbing phenomena, if you see here, for the when this is a bath, you say, and here a fluid is there. Okay, and this is the one which you are rotating with the velocity, rotational velocity raised to omega. And if you see that when it is Newtonian, then here you will be having curvature like this. Okay, so this rod is rotating. So for Newtonian, when it is elastic fluid, what you are going to get is there is this climbing effect. Okay, and this climbing effect, Weisenberg effect, right? And this climbing effect is happening because of this differences in normal stress, differences in normal stresses, right? So if you see this cone and plate rheometer having this so let me just see first. Yes, this one. The surface act as a sensitive manometer for a small negative pressure near the rod generated by the centrifugal force, right? This is the important outcome of this particular concept, is that this surface act as a sensitive manometer for small and small negative pressure near the rod generated by the centrifugal force that you are actually having because of the rotation, right? You are rotating it like this, and during the rotation the fluid is climbing up, right? And this climbing phenomena is happening because of the normal stresses, because in the direction of stress, here you are having shearing, but you are having the net force upward. Why? Because the normal stresses which are there, they are not getting nullified or getting actually cancelling out each other, rather they are existing. Now this rise can occur from the normal stress term to be understood. For R component of the equation of motion, you can see that you had this from the last lecture, right? And from the theta, this R component of equation, when you see this here, theta, theta, R, these are the normal components. And here you just solve this term a bit. You are actually differentiating partially with the respect to the R, and then you are splitting this term into the two parts using U and V for R and tau RR, and then accordingly you will get this one. So numerator of the second term here in the right hand side of the above equation is the first normal stress difference. So this is N1. So tau theta minus tau R. Theta minus tau R is the first normal difference, right? They will call it as N1 sometimes. And then if the gap between the cylinder is small, then what is happening? The del of tau RR divided by del R, which is tau RR at Ri minus tau RR at R0 divided by R0 minus Ri. You can write this. When the gap is very small, the curvature effects can be nullified, and then if you are not considering the curvature effect, then what you are going to face is the one this curvature effect is not there anymore. Then as if two cylinders are here and they are parallel to each other, right? And then this minus the rho of V theta square by R equals to del tau R by del R, this term, and comparing this here, the first term of this theta component of the moment equation is going to give you second term, you know, it is the first normal stress difference, but the first term can be written like this because the gap between the cylinder is small, and when you put all the values in one form, then you are going to see that if for the momentum we neglect the inertia effect, so V theta square by R term you are actually getting out, and then this tau theta minus R, so this became 0, and you can write this just like this, and here you know this is that. So now this, which is the first normal difference, which is tau 11 minus tau 22, can be written as tau theta minus tau RR, and this is coming out to be like this. And this, by the way, tau RR Ri minus tau RR R0 divided by R0 by Ri multiplied by R bar, these can be measured. So where R bar is the midpoint between, as I told that how this R0 plus Ri divided by 2 is becoming the point. So based on that, you came to know that this tau RR at the inner radius, right, and tau RR at the outer radius in the normal direction, their difference is non-zero, is simply the pressure difference between the inner and the outer cylinder. And we already seen that the first normal stress difference can be large positive number, right? And due to this, pressure on inner cylinder will be higher, causing the fluid to rise up to the rod. And there are several analyses. For example, the problem on the accuracy of the measurement of this. So tau theta minus tau RR, rod climbing, end effect, secondary flow, which is the Taylor instability, and then shear heating in the Couette flow, those are explained. So this was the example that has been discussed. So this was fairly simple example around the topic that was there in the second week. So if you see this, you will be provided with the omega versus torque, right? You need to be careful with the units because that can be played in the exams also. So always go for the SI unit, whatever unit is reported over there. And these values, if you see, they're based on this, and the ratio of the radii inner to outer, you came to know that this is the condition where you are having ratio to be 0.275, which is the K value, and it is below 0.99. So for the calculation, you can calculate the torque acting at the inner radii, and then accordingly you can calculate that the shear rate acting at the inner radii is for the given radii ratio, and you will have a table for this. So what you are going to do, first calculate Ri. So you will be having Ri, then you have to plot this omega versus ln shear rate, shear stress tau Ri, and this will, the slope of this will be coming out to be what? This is 2 omega, and the 2.73 is the slope that you are going to get, right? No, it's not slope. 2 into 1.46, which is the value of omega, what I mean, and then the slope of this, it is 2.73, the slope of this curve, which is ln of omega to the ln of shear stress, right? And this will be giving you the shear rate value. You have to just make the plot, the table of the shear rate calculated to the shear stress for each corresponding value of torque and the rotational speed, and then this shear rate and shear stress can be plotted. And looking at this curve, which is this shear rate versus shear stress curve, if you see, looking at this curve, we can see that these are anyway, let me just make it down. These curves are anyway non-linear, so it is not Newtonian fluid. And at the same time, if you compare this particular curve with the condition that we are having here, different conditions that we are having here is these are, so you will come to know that this is pseudoplastic fluid with n value less than 1, and then this particular thing, if you see, it will give you very exact interpretation. And the model, if it has been asked about which model it is fitting, it is basically Hartley-Berkeley model of non-Newtonian fluid, right? So let's see this one. So we have solved around 5 to 6 questions, and then all the questions we have solved step by step, and we have revisited the concept that was the main agenda of the entire week. And anyway, these are this advanced courses, so it will take some time, because it is sometimes become very difficult to follow up them within the week, within the given week, right? So coming to the next important topic of the week was this cone and plate rheometer. So this cone and plate rheometer, actually Moni and Evert, they started with that, but the most of the work and whatever the current this cone and plate rheometers are there, they are actually followed and opted from the Russell's work, which came up into 1946, right? So cone and plate rheometer is the most popular rotational geometry for studying non-Newtonian effects because of its constant rate of shear and direct measurement of the normal N1 by total thrust. So here, first difference of the normal can be very easily measured, right, using this cone and plate rheometer, right? So this is the geometry, very important. So in this geometry, just look at this. What is happening here? You are having a static plate which is circular anyway, and at the top you are having a cone kind of with same diameter, and this cone angle is very small, and the angles are given like this. Theta you are measuring in this direction, r you are measuring in this direction, and phi you are measuring in the horizontal direction, which is the direction of omega in which the rotation is happening, right? So theta phi r theta phi, right? So here you have to go for this spherical geometry for the calculation of the different parameters and the rheological property of the fluid, be it this the difference of the first difference of the normal stress stresses, and then the shear stress versus shear strain data, those things, right? So the basic assumptions here are listed. For example, for this particular geometry, equation of motion has to be opted for the spherical coordinate uh, because this is suiting the problem. And anyway, again, you will be messed up with the big equations. So these equations you can get from any transport phenomena book. Most of the time people prefer and go for this Bird, Stewart, Lightfoot, and any other transport phenomena book you can equally refer to. And then the assumptions are flow is rotational in phi direction, velocity component in the phi direction vary along theta and r direction. Okay, so v phi is the function of r and theta, right? But vr and v theta is zero. Like likely you had in the last lectures also, last sessions that you had, which in whichever dimension there is this rotation, only that is considered. Rest you are keeping zero in order to ease the calculation. And then steady, laminar, and the isothermal again. And then these isothermal and non-isothermal thing will be coming up in the next parts, which is this non-isothermal, where the heat transfer will also be taking place, or the mass transfer will also take place during the motion. So simultaneous heat and mass transfer or heat and mass and momentum transfer will be discussed in the later weeks of the course. So negligible body force is here. The beta angle is less than 0.1 rad, which is very less than, smaller than this 6 degree. And then the spherical liquid boundary you are actually considering for this. And symmetry is also there, because here the axis symmetry and symmetry is along del by del phi, right? So similar to the previous discussions that we had, in the r direction and theta direction and phi direction, you will be having the momentum equation, and then you will be nullifying most of the terms here, and only keeping the term which are leading to the normal shear stress, right? So this normal shear stress term is actually playing its role in dictating the anomalous behavior of the viscoelastic fluids, right? So for the theta dimension you wrote the momentum equation, and for the phi dimension you wrote the momentum. These are very simple. You just write the terms and implement the conditions. Anywhere you are having del by del phi, that will become zero. Anywhere you are getting vr and vr and vz, vr and vphi, that will get zero. Only I think v phi you are considering. So v phi will be existing, and vr and v theta will become zero. Okay, so accordingly the boundary condition here, one thing you have to notice is that the beta angle, what is the beta angle that you are taking? This is the beta angle that you are taking. So this position is what? Theta minus like pi by 2 minus beta. Theta equals to pi by 2 minus beta. It is 90. So this angle is what? Pi by 2 minus beta will give you theta, and accordingly you have to actually recreate the equations that were there. So accordingly, if you solve it, v phi will come as omega into r into sine pi by 2 minus beta. And this sine pi by 2 minus beta can be written in terms of cos, which is cos beta. And the expansion of cos beta will, when you expand this cos beta, it will give you 1 minus beta square by 2 factorial plus beta to the power 4 divided by 4 factorial plus so on. So these 2 or 3 terms you will be taking based on the value of beta. So that's why the angle is taken very small for this cone and plate geometry, because these terms, whichever is important, you will be taking, and rest you are actually omitting out, right? So shear stress calculations you have to make. So you came to know that this is 3m by 2 pi r cube is the shear stress. That is actually important, and this is the shear rate value that you came to know after the calculation. So these are very simple calculations, just very dangerous equations are there. So these equations are, anyway, if you follow each step, you are going to get it easily, right? So coming to the equation, that a question that we were solving was this one. I think it is I think it is fourth question, right? So let me just take new slide. It's fourth question. So here the angle you are having 1 degree 18 minutes and 45 seconds, and then the cone and plate rheometer radii is 25 mm, right? So this is 25 mm. If you see, this is the radii, which is 25 mm, and the angle, cone angle is what? So what is the cone angle? This is the cone angle, right? Or this is the cone angle. If you see the smaller, so 1 degree means very small, so beta is your cone angle. I think that you have to take care, because that is very important in order to actually start solving the question. If you are actually feeling this beta I am talking about, and this is this beta, so this is cone angle, right? And this is very small. So if you see this, so let us solve this question. And once you see solution I am having anyway, but the main thing is following each step, not letting any steps out, then you will come to the end. So let me just increase the thickness. Yes. So in this one, for a cone and plate, okay, rheometer, right? For a cone and plate rheometer, and here the angle is 1 degree of a small angle, so that you can write angle. So what angle you have? Beta equals to 1 degree 45 minutes or some seconds you had, right? What was that? 18 dash 45 double dash 18 dash 45 double dash, right? So this, the shear stress, the shear stress, this can be calculated as tau theta phi, and this is equals to what? The number that we had at the end, what you got? 3m by 2 pi r cube. So 3m divided by 2 pi r cube, and this is the radius of the cone that you are actually calculating. 3 into this m value, what was there? 3.97 into 10 to the power minus 4. So 3.97 into 10 to the power minus 4 divided by 2 into 3.14 into this ri. Again ri, r, you know, r is what? R is 25 mm, that I have written here. So this r is 25 mm, which is 25 into 10 to the power minus 3, okay, minus 3 cube, right? So it will give you 12.14 Pascal. You are getting this. So this is the B option is correct answer, right? So this is the one thing that you have to solve. So now the next question we will be solving, which is on same thing, but just the angle is different here, and the rotational speed here is 0.1. Here it was different. Here also 0.1, 3.97, 3.97. What is the difference now? Lower edge of the cone you have been asked calculate. So what difference in this question you are having? Of a small angle, the shear rate is this. Okay. In this one, what is the value of shear rate at the lower edge of the cone? Okay. So here cone angle is small. At the last problem also you had cone angle of smaller dimension. So in the last question shear stress was calculated, right? But here you are going to calculate shear rate. right? So this is important. So only difference you are having is shear rate calculation, right? So there you calculated shear stress. So these two information is important. So you just solve this for some time, and then please put your solution in the comment, because so you just attempt it in the comments. If you put your trials, then it will be easy, right? So you just try it once. So after this we are having few more questions. So like this is the 6th question, 7th question, and then some theoretical question which will be very easy to solve, and again some numerical problems. So around 12 problems we are having. Okay, so again half an hour is remaining, so we will be solving them step by step, and I will give you some problems to solve from your own at the end, right? So these are a bit lengthy, but anyway we are revisiting the concepts that was taught. So this will be revision kind of session. So anybody who left, or because of some reason they haven't watched the the video, they should actually first watch and then come to this session. This will be recapping you entire week within a 2-hour session with some examples, right? So for this question, if you see, let me just remove it. If you see this, for a cone and plate rheometer of a small angle, for a cone and plate rheometer of a small angle, right? Small angle. What was the shear rate that was discussed? You just have to calculate the omega divided by angle beta. That can be written. So 0.1 divided by 0.02. Okay. So this is 0.02 that you are getting, and this you will get as what? 5-second inverse. Why? Because this beta equals to what? You had 1 degree, 18 minutes and 45 seconds. Now, when you convert it into degree, you are going to get 0.0 T rad. Okay, so this minute and then second. So you start from the second, then convert them into the minute, and then again convert them into the second degree. You will come to know this is very simple class thing, and then you will be getting your answer to this problem, which will be 5s inverse, which is 5. The inverse is the shear rate. So what is the correct answer? You see, D option is the correct answer. Okay, D option is correct answer, right? So coming to the next one. So we will be now solving only questions. So somewhat, if somewhere it is needed, I will go to the slides. Okay. So now the parallel disc rheometer, which was the last lecture of the week, and here you came to know that instead of having cone at the top, which is shearing, now you are having disc only, and then the the distance between two discs here is 0.7 mm, which is very less, around 700 micrometer you are having, and then r equals to 25 mm, right, is used to investigate rheology of fluid by rotating the top disc at the 140 into 10 to the power minus 4 radian per second, and the corresponding torque is 45.4 into 10 to the power minus 5 Newton meter, right? What is the value of shear stress in Pascal unit? It is required. So a parallel disc rheometer with h equals to 0.7 mm and r equals to 25 mm is used to do so. So if you see the geometry of that rheometer, this is a disc, and this disc is rotating at rotational speed of omega, and this is another disc, and this disc is static disc, right? And then distance between these two discs, which is h, and h is equal to 0.7 m, and then radii of this disc is what? 25 m, right? And this is used to measure the rheological fluid property, right? And then this omega value is given as 140 into 10 to the power minus 4 radian per second. The torque value they have also given is 45.4 into 10 to the power minus Newton meter, right? So you have to calculate the shear stress in Pascal units. So first just revisit very fast the same. Okay, so this was some remaining portion of that core and disc. So you came to know about that if this shear rate is nearly constant for the small core angle, shear stress and shear rate also nearly constant as shown in the figure, and then that can be used. So about the normal stress difference calculations you had, and there was one example that you solved for this small angle. So similar problem we are solving now. Okay, and this is the third last, like last the video of the third week, and here you had revisit of all the lectures. Along with that, the cone and plate rheometer for this rheology measurement of the fluid, and you came to know that we have just solved a question around this, and then this is this first normal stress difference. So whenever you will be asked the first normal difference, you will be given with the thrust value. Okay, so in the exams you may expect this thrust related problems, and this thrust related problem will be used in order to calculate the first normal difference in the case of this plate and cone type rheometer. Okay, so parallel disc rheometer for now we are considering, and why this is, most instruments are designed to permit the use of either geometries, and contrast to cone plate flow between the parallel disc is not homogeneous, right? And this is the geometry that we were talking about, and here you have this steady laminar flow and isothermal condition as same. V theta rz will be there, so you are considering the cylindrical coordinate, and then this negligible body force you are considering for your problem. So coming to the main equations, which was the theta component of the equation of motion, which will be give you this normal shear stress distribution, and then this r directional equation of motion has been solved. So the main thing is, after applying Leibniz and everything, you will come to know that if the test liquid is Newtonian, then what you are getting, tau theta r 2m by pi r cube, right? But if it is non-Newtonian, then what you are getting, tau theta z r m by 2 pi r cube, and this is the correction factor that is coming into the picture, right? And this is actually going to dictate the effects that you are getting, and the value of normal differences, stress differences that you are going to calculate at that, right? So if you see, let me just put it here, and these all videos are recorded, so you can revisit them, clarify your concepts, and reappear in the next assignments, and finally probably in your exit exams for the certification. So this is the sixth question that we are going to solve, and about parallel plate and disc. And here this value you are given with, which is 0.84. right? This value you are given it. So if you remember, and the discussions that just now we have done, let me just remove it very fast. I will be solving now all the questions. Is this shear rate, in this case shear stress for parallel disc rheometer, parallel disc rheometer meter is what? Tau equals to m divided by 2 pi r cube, right? And this is 3 plus what? D ln of torque divided by D ln of omega, right? And this value you are given. So what? M you are given, 2 pi you are given, R you are given, and entire this factor was the main thing. If they have given this M versus this data, then you would have had to draw this curve and then get the slope for ln versus M by omega curve, right? But here exactly you are given with the data. So 45.4 into 10 power minus 3. What was that? Minus 3 minus 5. So it's minus 5, right? Divided by 2 pi. And now the radii you know. Radii was 25 into 10 power minus 3. It is cube, right? And 3 plus 0.84 is the value that you are given with. So once you solve it, you are going to get 17.77 Pascal. Okay. So this is the shear rate that you are going to get. So I think 17.77. So D option is correct. D is correct. Okay. So coming to the next question. Very less time we are with. I think only 15 minutes is left. So let us solve it very fast. A parallel disc rheometer with the H equals to 0.7 R is this, used to investigate the rheology of this. The value of shear rate. So you have to solve the shear rate in this given problem. And if you remember the rate of the shear rate for the parallel disc, disc rheometer, right? What was the shear rate? This is R divided by H into omega, right? And when you solve it, 25 into 10 power minus 3 divided by H was 0.7 mm, means 0.7 into 10 power minus 3 multiplied by omega. Omega is what? 140 into 10 power minus 4. You will get 0.5 second. So this is the so it is coming to 0.5, right, per second, right? So 0.5 per second. A is correct answer here. So now if you see, the next question is this 8th question, which is in concentric cylinder viscometer, the shear stress of the test fluid is independent of the torque, inversely proportional to the torque, directly proportional to the torque, right? All of the above are correct. So which is correct? You just see it. So what you are saying is option A. Somebody wrote right. Somebody is saying option A. Independent of torque. It is dependent on torque. Inversely proportional to torque. Directly proportional to torque. All of the above. So the expression, you should just remember the expression that we just discussed. Concentric cylindrical viscometer, the first class of the week, you came to know that this torque was the m factor, and you had this tau equals to m divided by 2 pi lr square, right? So this m is directly proportional, right? So it is directly proportional to the torque that is there. So let us get that answer here. So this is the one that we are talking about. If you see, this is r square h, right? H or L, it is there. So if you see in the concentric cylindrical rheometer, this is the 8th question, right? Let us keep it there. This, Okay, let's get it here. Okay, so in concentric cylindrical viscometer, the shear stress of the test fluid is directly proportional to the torque applied. The relationship is fundamental to the operation of such viscometers, where torque measurement are used to calculate shear stress and the subsequent viscosity, right? And then understanding the relationship, what you have to understand is this: in the concentric cylinder or the quet viscometer setup, one cylinder, either the inner or the outer, is rotating, while the other remains stationary, right? So whichever is remaining is stationary. If you see whichever is actually stationary, there you are having this no slip conditions. Okay, so anyway, in that direction you don't have to actually see, right. So if you see, while the other remains stationary, the fluid fills the gap between these cylinders. As the rotating cylinder moves, it applies the tangential force to the fluid. That was the thing we were talking about, the v theta component which was there, is applied in the tangential force to the fluid, generating a shear stress. The torque required to maintain this rotation is directly proportional to the shear stress experienced by the fluid. So this is the mathematical form that we had. This tau equals to what? Mi divided by 2 pi ri square L, right? And here all the terms are given. So given this understanding, so incorrect, so C option is correct answer. A torque increases, shear stress is proportional. So option C is correct answer, right? So we will have C option to be correct answer. So now the next question we are going for is this ninth question, and the ninth question is: in the concentric cylinder viscometer, the shear rate of the test fluid is what? Directly proportional to the rotational velocity, inversely proportional to the rotational velocity, or there is this none of the above, A, B, C and D. C, right? Which of the following? Concentric cylinder viscometer, the shear rate of the last question was about shear stress, and this is about shear rate. And then similar questions you can expect in the exams also about different. So here you have been asked about this concentric cylinder. Maybe there you will be asked about cone and plate geometry, and then subsequent cylinder plate kind of rotating geometry. Or sometimes in the exams also you will be asked about when the both the cylinder, both the plate, bottom or top, both are rotating, right? So for those things you have to get prepared. So the ninth question, if you see, I will be frequently taking you there, and this is this one. So I have just made the solutions so as to keep the things in line. So here if you see, the shear rate, if you remember, in the concentric one was directly proportional to the rotational velocity, independent of the rotational velocity, inversely proportional to the rotational velocity. Shear rate and rotational velocity, it is very clear that if more is the rotational speed, more is the shear rate. So it should be directly proportional. So that's what we will be looking at. So a practical source further states that the speed of the rotation of this conveyor is proportional to the shear rate experienced by the fluid. So shear rate in the concentric cylindrical viscometer is, in the concentric cylindrical cylinder of the viscometer, shear rate is directly proportional to the rotational velocity, which is angular velocity of the moving cylinder. This relationship, together with the instrument geometry, determines where the actual shear rate is experienced by the solid. So there are some points in the Wikipedia also. So those things you can consider, but in the exams and in the lectures, sir has already explained that this is coming from this particular thing. Let me just take you to that. This is first week, and here or the second week revisit. In the second week, first slide was the revisit of whatever you have learned. And if you see here, these shear rates, they are directly proportional to this omega, which is rotational speed. So all these shear rates are directly proportional to what? Omega, right? So let us take that to that place. So it will be a kind of solution for the shape, right? So let us just take it here in the slides. So these equations tells that the speed is directly proportional to the rotational speed. So this is directly proportional. Shear rate is directly proportional to the rotational speed. So A is correct answer. Correct answer, right? So that's one thing. And then coming to the next question is that there is three more question, and again this question I will be leaving for you because similar questions we have solved. This cone and plate rheometer having this 20 mm of radii, and then this cone angle of this used to investigate the rheology of this of an unknown fluid at the room temperature while the cone is rotating at 0.1 rate radian per second. The corresponding torque is 3.97. What is the value of the shear rate at the lower edge of the this? So what is the difference between the question that we have already solved and this? Is one is this the radius of the cone? Okay, one is this radius of the cone, right? And another thing is what? The radius of the cone is one thing, and another thing is another thing is this the torque is same, the angle is also same, just the radius is different, and the rad is also same, and you are asked about shear stress at the lower edge of the cone. So it is very similar to the questions that we have solved. So similar to what? It is very similar to what we had in what? Shear stress value. Same as fourth question. Same as right? So here also you will be using 3m by 2 pi r square value. So 3m by 2 pi r square value. So I will be telling you answer. You will get A as an answer. A is correct. You just solve it. You should use this tau equals to what? 3m by 2 pi r cube, right? And this is similar to the fourth question that we solved. I just kept it for you to just revisit whatever concepts we had already have gone through, right? A parallel disc rheometer with H 0.5 mm and R 25 mm is used to investigate rheology of the fluid by rotating the top disc at the 140 into 10 to the power minus 4 rad per second, and the corresponding torque is this. What is the value of shear rate? So this question also we have had, like there was some discussion about the same, but I will be just giving you hint about the same question that which will be helping you to solve it, right? So the question 7th we have solved, and that question was very much similar to this. So this question 7 is similar. So you may refer to this. So I just kept these questions for you to solve, right? So the 10th question is similar to the 7th one, and answer to this I will just tell you so that you can match it with yours. Answer is A option, which is 0.7 seconds, right? So 10th and 11th is done. Last question is 12th, and again this 12th question is also similar to what we have already solved today. So it is similar to what? So the answer to this will be C option. C is 12.61 pascals, and this is similar to what? Concentric cylinder viscometer. Concentric cylinder viscometer, and this is what? This is similar to first question number 1, right? So this is same as same, right? So this was all for today's class, and you are welcome to put your queries and things. So if you want to access this Q&A sessions, like this QA and A, here you can go and you can use the discussion forum. So whatever queries you are having, you can use the discussion forum. You can get connected to us, and then you revisit these videos. These videos will be anyway posted, and you can have comments on this over that. And then what, before coming to this particular session, you should actually watch all the lectures, because otherwise it will become a bit clumsy going to the instructor and then coming back to the revision session and this recap session. It will be helping you, and then step by step solve the numericals that are being provided to you. Anyway, these numericals, whatever questions you are these are just similar to the one that sir is teaching in the class, and that is probably as in the exam. The course is very vast. Whatever equations that you are dealing here is a bit lengthy or of high volume. So many times you will be given, you will be provided equation, either it is the cylindrical coordinate momentum equations or the spherical coordinate momentum equation, and if one or two questions are getting formed from there, you have to be actually thorough with the conceptual understanding, how the different terms you are letting or omitting out based on the system that you are dealing with, right? So that is it. Next week is what, week 4, and you will be actually, so the week 4 will be helping you to revisit all the fluid mechanics and heat transfer balance equation concepts, right? So all the derivations you will be revisiting, and you will be saying that what is the moment what is the part where this non-Newtonian fluid will be entering up into the picture of whatever studies and the concepts that you had under your during your undergrad and PG MTech courses, right? So thank you so much for your kind attention, right? Thank you. So you go through these videos, and I will be not disconnecting the call. Okay.